In section 6.6, we'll be discussing applications to physics and engineering. Among the many applications of integral calculus to physics and engineering, we consider three: work, force due to water pressure, and centers of mass. As with our previous applications to geometry, areas, volumes, and lengths, our strategy is to break up the physical quantity into a large number of small parts, approximate each small part, add the results, take the limit, and then evaluate the resulting integral. Work. Now, the term work is used in everyday language to mean the total amount of effort required to perform a task. In physics, it has a technical meaning that depends on the idea of a force. Intuitively, you can think of a force as describing a push or pull on an object. For example, a horizontal push of a book across a table, or the downward pull of the Earth's gravity on a ball. In general, if an object moves along a straight line with position function s of t, and the force F on the object in the same direction is defined by Newton's second law of motion as the product of its mass m and its acceleration. So there's definition number one. F is equal to m times the second derivative of s with respect to the second derivative of t. Now, in the SI metric system, the mass is measured in kilograms, the displacement is in meters, the time is in seconds, and the force is in newtons. Whereas newtons is kilograms times meters per second squared. Thus, a force of 1 newton acting on a mass of 1 kilogram produces an acceleration of 1 meters per second squared. In the U.S. customary system, the fundamental unit is chosen to be the unit of force, which is the pound. In the case of constant acceleration, the force F is also constant and the work done is defined to be the product of the force F and the distance d that the object follows. So for definition number 2, work is equal to force times distance. Now, if force is measured in newtons and d in meters, then the unit for W is a Newton meter, which is called a joule. Now, if F, the force, is measured in pounds and D is in feet, then the unit for W is a foot-pound, which is about 1.36 joules. Now, for instance, suppose you lift a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. The force you exert is equal and opposite to that exerted by gravity. So from equation number 1, force, which is equal to mass times gravity, which is equal to 1.2 times 9.8, which gives us 11.76 Newton. Now in equation 2, it gives the work done as work is equal to force times distance, which is equal to 11.76 times 0.7, which is approximately 8.2 joules. But if a 20-pound weight is lifted 6 feet off the ground, then the force is given by F, which is 20 pounds, and so the work done is 20 times 6, which is equal to 120 foot-pounds. So here, we didn't multiply by G because we were given the weight, a force, and not the mass. Now, equation 2 defines work as long as the force is constant, but what happens if the force is a variable? So let's suppose the object moves along the x-axis in the positive direction, from x is equal to a to x is equal to b. And at each point x between a and b, a force f of x acts on the object, where f is a continuous function. Now we divide the interval from a to b into n subintervals with endpoints x subscript 0 all the way to x subscript n, and equal with delta x. Now we choose a sample point in the ith subinterval, and then the force at that point is f of that value. Now if n is large, then delta x is small, and since f is continuous, the values of f don't change very much over the interval. So in other words, f is almost constant on the interval, and so the work that is done in moving the particle from x subscript I minus 1 to x subscript I is approximately given by equation 2. So the work subscript I is approximately F of that value x subscript I times delta x. Thus, we can approximate the total work by making that now into a summation. Now, it seems that this approximation becomes better as we make n larger. Therefore, we define the work done in moving the object from A to B as the limit of the quantity as n approaches infinity. Now, since the right side of equation 3 is a Riemann sum, then we recognize its limit as being a definite integral, and so therefore it becomes the integral that goes from A to B of the function dx.